one of the very important issues now is the fact that the climate change, or I would use the word warming here, how is the water cycle going to change? And from most accounts, the rainfall is not going to change with increase in temperature. It's probably going to be the same. But the cycling of rainfall becomes faster. That is, the residence time of water in the atmosphere and in the soil decreases. So it's faster and faster. So it's almost like there is no residence time, and that results in greater extremes of weather. By weather, I mean more floods, more droughts, more hurricanes, more tornadoes. So that's the real danger from climate change. So we are trying to track these patterns using long-term data sets from satellites, as well as doing some amount of modeling and some amount of in-situ observations. I think one of the most exciting things I've been involved with very recently, I've been working on a world water plan. We're talking about world availability of water. Now, North America may not be the first one affected, but globally, if you look, the biggest problems arise because of lack of adequate fresh water in urbanized centers. So if you look at the big cities in China or India or in Southeast Asia or even in South America, even if the population does not increase to the 10 or 12 billion envisaged by 2050, the population distribution is going to change dramatically, and people don't focus much on the distribution. So there are more people living close to the city, and as a result, they have less access to fresh water, clean water. So you will have a greater amount of waterborne diseases. Now, this is not climate change per se. It's the climate change tempered with human population increases.
I think we will adapt in some way. Always the question is adapt at what cost? At what cost to the ecosystems we like? Aquatic habitat. How much will we give up of aquatic habitat to give water to people? The people will win. It's clear. All right? But how do we make those decisions, and how do we make them wisely and with foresight, understanding the implications of our actions? I think that's been the problem in our traditional water resources management. We solved the problem at hand, but may have created a lot of other problems. And it's trying to make those decisions in a more informed way. I think that's what the science is really there for. Ultimately, there's policy decisions to be made. Society has choices to make. It is a finite resource, and I think we're beginning and coming up against that finite resource.
And that really is one of the directions that the science is going, is to become sophisticated enough in our understanding of the processes to be able to have the models to do more forecasting of where the Earth is evolving to.
What I'm particularly concerned with is to bring together the water data that we have. And the reality is that the agencies that collect water data, like the US Geological Survey and the EPA and the state agencies, and even individual investigators, everybody just does it their own way. They publish their data on the internet with some website, some way. There's no standards at all. So what we've done in our quasi-hydrologic information system project is invent a language for communicating water data on the internet called WaterML. And it's like HTML, it communicates text and pictures, while WaterML communicates water data like precipitation and stream flow and water quality data. It's like Home Shopping Network or Travelocity. When you go to Travelocity or Home Shopping Network, you don't care what's going on behind the scenes. You just want to buy something or make a trip, right? Well, the same thing with water data. You just want to say, I want to get the water data. I don't want to care that it's measured by this agency and they do it this way and another agency does it the other way and some university people do it a third way. I just want to get the data.
A common theme throughout all areas of research is the need for the development of future Earth scientists. Here in Vermont, the STREAMS project integrates research scientists, graduate and undergraduate college students, as well as high school students and their teachers in a network of data collection.
The STREAMS project is a project focused on educating young scientists and looking at streams and rivers in Vermont.
Whenever you gather a data set like this, you've got a snapshot in time, and it's always interesting for future scientists to get hold of that data set.
I'm Kathy Joe. I'm the STREAMS project coordinator. Our goal is to both gather data, but then also get lots of people interested in science. So yeah, it's a big operation. The STREAMS project has many, many people involved. We have faculty members that are overseeing specific teams of people. So there's teams of people working at other colleges, and the faculty will oversee a couple undergraduate students, and they'll work on a specific research project. Like at St. Michael's, they work specifically on all the macroinvertebrate communities.
I'm Declan McCabe. I'm an associate professor at St. Michael's College. The students on the Streams project have all been very, very excited from day one. So it was really exciting for me to see the excitement in them.
So we're summer interns for the Vermont Streams project. Our job is to collect macroinvertebrates that are indicators of species, or indicators of species of health of the water in Lake Champlain.
I think for me, working with the high school students has been particularly rewarding. Seeing their faces when they pick up a rock and notice bugs on it, and telling them that those are indicative of a certain pollution. A lot of times people think back to their high school biology class and it was reading out of a textbook and mixing things up in beakers. And to give people a real world application to science is really interesting for most of the high school kids. They loved it.
I'm Evelyn Boardman. I'm a student at Rice High School, and I found a brochure about the Streams project, and I enlisted my mom, who's a science teacher, and my friend Kari.
My name is Kari Foote. I'm a senior at Rice High School, and I got involved in the Streams project when my friend Evelyn asked me to come. She said macroinvertebrates, and I've always been fond of bugs, so I was like, sign me up. And every 2 weeks we've been coming down to our 2 stream sites and we've been collecting water samples. Part of the reason that's great to talk to college students is people who are going into environmental fields of science in the future want to have an idea of what they're looking for, and interacting with the graduates kind of gave us a good idea of what kind of majors we might want to look at and kind of what the college scene is.
I'm Sharon Boardman. I'm a teacher at Rice Memorial High School. I teach science. I've actually learned a lot, so it's added to my base knowledge, which will help me, I think, be a better teacher.
I think science is a hard thing to avoid. I really don't understand people who can kind of separate themselves from it, because it's something that once you kind of get a taste for it, you really can't get it out of your head. Like, you're walking down a stream and you think, I wonder if there are macroinvertebrates in that riffle. But I think it's going to take a special type of student to understand what we're talking about. Yeah. One who's interested in the world around them.
We send out our teams of high school students and undergrads to go collect information about the water quality in those streams, as well as the biological communities.
No one high school could do that on their own, but collaborating with 13 or 14 other high schools gives you the ability to have replication as a scientist would want. You can't really replicate that well when you're doing your science within the context of your biology course. You need more power, you need more people, and that's the power of the data set.
It's been fun to watch all the faces of the high school students when we go out to the streams. You know, when you pick up a huge bug and go, ah, it's really gross. Or, you know, some people are really excited to look at them under a microscope, or some people are really excited to look at, you know, how much phosphorus is in their water sample, or, you know, do the math, do the equation and see what you come up with. So there's all sorts of opportunities to encourage future scientists.
NSF's primary mission is to advance knowledge. The terminology geology or earth science means a lot of different things to a lot of different people. Some people think earth science is very narrow. Others see it as more broadly encompassing of the atmospheric and the ocean sciences, even space science and planetary geology. But within NSF, it is encompassing of all of those fields. A lot of people are beginning to recognize that those global skills are actually really important to not just being a scientist, but other fields and endeavors. The world is very interconnected, as we know, and one of the real values of a geoscience education is that you are a systems thinker and you're thinking globally.
Water is not contained by geological boundaries or cultural divides, and like most areas of scientific research, we're finding that approaching water research from single discipline thinking is no longer acceptable. Traditional scientific divisions need to be eliminated in favor of an interdisciplinary approach. Only through collaborative partnerships will we be able to design a sustainable future.
The future conflict is going to be a water conflict. It's not any other. If you look at the local market, you buy a bottled water for how much? And then if you look at a gallon of fuel is how much? You pay more for water than fuel if you relatively look at it, And in the future, we don't have this fresh water, The fresh water is gradually decreasing. And, as long, unless otherwise we protect what we have now, and save it for the next generation, we are going to face a problem. So how can we help each other? The agricultural community in some places under stress right now. We are all contained in a closed loop, a closed system. We have to think beyond our local area, because the world is, whatever air that we breathe, everybody can have that air everywhere. So that's what I'm trying to promote. The science doesn't have any border. The research doesn't have any border. So we have to work together to save this environment and be able to pass it to the next generation. That's my philosophy. That's my wish.
We look to technology to clean water over and over and over. There's a really strong possibility that technology can only do so much, and bringing in that technology creates a lot of problems in and of itself. I had two influences that were very important to me. One was growing up without running water, and the other one was a grandmother who had a very rich mythology in water. Perhaps one of the least explored adaptive strategy for us is reintegrating water into our culture. We have commodified water. We've turned it into a thing, something we get and use, and we've disconnected it from our culture. When you do that to a resource, you end up making decisions on it in ways that are not sustainable. We all had water integrated into our cultures, and in many cultures not that long ago. So perhaps one of the best things we can do is bring water back to our daily lives beyond a commodity.
Ensuring a reliable water supply for personal consumption, agriculture, and industry may be the most significant issue of our times. As we start to comprehend the concept of peak oil, we may also find that peak water is fast approaching. And while humans can adapt to the end of the petroleum era, we simply cannot survive without water. Scientists are optimistic that we can address these challenges by incorporating modern-day technology with contemporary science and establishing water as culturally significant. I'm Amy Seidel. Join me next time for more Emerging Science.